Hello, class. This is Mr. Hart. And in this podcast, we want to start our discussion of impulse, which is the next part of our momentum unit. And we've talked about what momentum is, but it's not really a useful quantity until we talk about what impulse is. Okay? An impulse is a change in momentum. Okay? I often think about, like a football tackle, for example. Someone's moving in one direction, suddenly they get hit, and then they're moving another direction, right? Their momentum is going to change. Okay? So impulse is a very useful quantity because it helps us describe collisions, right? This, football tackler is tackling this guy, right? There's a collision that occurs and the motion is changed because of it, okay? Being able to describe that is through impulse, okay? So if we look at the equation for impulse, it's really simple to describe. Impulse is simply just a change in momentum, okay? Now in this form, it's still not very useful because all it is a definition. Okay, impulse equals momentum. So let's think about what this means, a change in momentum. So in the last lesson, we defined momentum as mass times velocity. So a change in momentum would be a change in the mass times the velocity. Okay, so if we think about it, your mass often isn't going to change, right? People don't just suddenly lose, 50 pounds or whatever, right? Your mass isn't going to change in a collision. So we can move the delta sign inside so that just the velocity is changing because the mass won't change. So the change in momentum or impulse is equal to mass times change in velocity. Okay. Now this is a little bit more useful. We're almost getting there. Okay. We're going to take a couple more steps and then we'll get to an equation that's very helpful to use. Now we're going to replace this mass with F over A because if you remember, F equals ma from Newton's second law. So we can move the A down here, right? So then the mass equals force over acceleration. So we're going to replace m with that, okay? Which leads us to this version. So change in momentum equals force over acceleration times change in velocity, okay? Now we're just going to simply move the acceleration underneath the velocity, okay? So we get force equals change in velocity over acceleration, okay? And then if you also recall that we define acceleration as velocity over time, then by the same definition, if you just move t and move the a and switch places, t equals velocity over acceleration. Okay, so this part right here turns into that part right here. So you got f times t, or change in t. Okay, and then one last step is we replace change in momentum with our original definition of mass times change in velocity, and then we get to the very useful equation. Okay, this is the impulse equation that we want you to know, okay, that I want you to memorize, okay? And to help you memorize, I call it fat MAV, okay, if you just imagine the delta signs or A's, okay? I don't know why, but that seems to stick with students, so just call this the fat MAV equation, okay? But here's what it means. The force times the change in time equals the mass times the change in velocity. Okay, this is an incredibly helpful equation because we can describe collisions based on how long the collision is occurring for, how much force is involved in collision, and that will tell us how much their velocity is going to change in that collision. Okay, this is a great equation for connecting the force and momentum ideas, right? We kind of said, oh, force and momentum aren't necessarily related, okay? But in reality, they always are kind of interconnected, and this is one example of that, the fat MAV equation. Okay, but very helpful in describing collisions that occur. Okay, let's go ahead and look at an example problem. Okay, a force is applied to a shopping cart with a mass of 7 kilograms for 5 seconds. The shopping cart goes from rest to 15 meters per second in that time. Okay, so we're applying a force for a certain amount of time. Okay, what is the magnitude of that force that causes this? Okay, well, let's see what we got. So we know that the mass is 7 kilograms. We know that the time, or change in time, the length of the collision, I guess you could say. It's not really a collision in this case, but a force is being applied for a certain time, okay, is 5 seconds. And then the change in velocity is from 0 to 15, so that's just going to be 15 meters per second, okay? Then we write down our equation, fat MAV and then we need to figure out what we're solving for. Okay, so we're trying to solve for the force. Okay, what's the magnitude of the force? So we're just going to take the T and put it down there. So F equals mass times change in velocity over change in time. And that's going to give us 7 kilograms times 15 meters per second over 5. So if you put that in the calculator, you should get that is equal to 21 newtons, okay, because it's a force. So let's just quickly make sure that the units work out here, okay. If we think about it, the mass was in kilograms. Okay, 7 kilograms. The change in velocity would be meters per second, and the time would be in seconds as well. So kilograms meter per second, well, that's the same as a kilogram meter per second squared. And hey, guess what? That's the same as a newton. Okay, so the units work out in this case. Okay, and they will always work out if you keep your units in SI. Okay? All right, let's try another one. So pressing on the gas pedal applies a force of 5,000 newtons on a car. If the car has a mass of 1,250 kilograms and the driver hits the gas pedal for 10 seconds, what will be the new speed of the car? Okay, so you're flooring it, right? You're driving your car, you're flooring the gas pedal. How fast will you be going after 10 seconds? Okay. So again, let's write down what we know. So we know the force is 5,000 newtons. We know the mass is 1,250 kg. The change in time is 10 seconds. So this time, let's just make sure, yes, those are all SI. We write down fat MAV. And this time, we're looking for the change in velocity. Okay. So what we need to do is take the mass, put it down there. So we get the change in velocity equals F times change in T over the mass, right? So we bring that down there. So that's going to give us 5,000 times 10 over 1,250. Okay. Put that in your calculator. And you should get that your new speed is 40 meters per second, okay, or about 80 miles per hour. So you're on the freeway basically at this point. So there you go. That's another use of the fat MAV equation, but you can see how useful this equation can be because these are easy measurements to find, right? The force is easy to find. The time is easy to find. The mass is easy to find. A change in velocity is easy to measure, right? These are things that we can easily detect. When we were working with just force equals ma, the acceleration of an object's really hard to measure directly, and so it wasn't quite as useful. We don't usually describe things in acceleration, but these are all things that are easy to measure, so it makes this incredibly useful for us. Okay. All right, let's think of one more scenario with impulse. Okay, this is actually a true story. One day I'm at this neighborhood party, and one of my neighbors just kind of decided to bring a potato cannon. I don't know why, but he thought it was cool. So he brings a potato cannon, he's launching potatoes into the air, and then after a while he's like, hey, let's put this beach ball on this cannon because it's so light, it's just going to go flying. Okay, but the thing's huge. The cannon only has a small nozzle like this, and it has the huge beach ball. And so I look at it and I'm like, that's not going to go anywhere because of impulse, okay? But he's like, no, this thing's so light, it's gonna go somewhere, right? It's gonna go flying because it's so light, okay? So the question is, who is right and why? Well, I wouldn't be asking if I wasn't right. So yes, I'm right in this case because of impulse, okay? So if you think about it, if you have that cannon, let's say this is the nozzle of the cannon, okay, and you have the huge beach ball on top, okay? According to the equation, if we want a change in velocity, we need a force and a change in time. Now, the guy was correct that, yes, this is going to have a large amount of force, but if this is just barely sitting on the top of the cannon, this change in time is going to pretty much be zero, right? There's not going to be a change in time. It's going to hit for a millisecond and then be off the cannon, okay? So even though, yes, the cannon has a large amount of force, there's no change in time, so the end result is there is no impulse, there is no change in velocity, so it just kind of plopped off the cannon. Okay, that change in velocity was zero. Okay, so you have to have an impulse, you have to have that change in time. The reason the potato cannon works so well usually is because you get that small chunk of potato, and you shove it down in there as far as you can, right? And so it has that whole time it's in the cannon where it gets that force. And that gives it a change in impulse, and that's what causes the potato to launch and have a change in velocity. Okay. So moral of the story is, don't put beach balls on potato cannons, and I'm always right when it comes to physics questions. No, I'm just kidding. Anyways, let's move on. Let's look at some other applications of this. Okay. A question we talked a lot about in class is, how do we make cars safer? What do they do to make cars safer? Okay, and one of the big things they do is they have understood this idea of impulse. If you watch movies with like old car chases and you watch the old cars collide with each other, they don't have any damage to them hardly. Okay, they used to build them with these super strong steel and iron frames on the car, so there was minimal damage to the car itself. But they realized when that happened, when those collisions occurred, the car would be fine, but then the people inside of it would be dead. Well, why is this? If you think about it, it's because of impulse. Okay, let's say you have two cars coming at each other. Okay, and I know I'm not a good car drawer. I apologize. But you got two cars coming at each other and they collide. Okay, they're going to hit each other at full speed. Okay, if you want less force on you, right? Let's think about fat Mav. If you think about it, this is going to be fixed, right? The mass is going to change. Your change in velocity is not going to change. Okay, you're going to have that collision occur. But if you want this to be low, the force to be low, you got to make the change in time high. Okay. So how do you do that? Well, it's not from having a nice strong steel frame that only hits for a couple milliseconds. You want your frame to be colliding with the other car for as long as possible. So if you watch car collisions nowadays, okay, you'll notice that they'll start to collide and they'll kind of collapse in on themselves, right? They'll kind of fold in and crunch. Okay, that's not because the car was poorly designed. In fact, it was designed intentionally to do that so that the time of collision is increased. Okay, if you can increase that time of collision as much as possible, then less force is going to be applied to the pedestrians. Okay, so it's kind of unfortunate because it means there's more cars that are totaled now. It costs more, but we save more lives that way, and that's the more important thing, right? So if you think about it, we want that collision, or when that collision occurs, we want the car frame to compress, to kind of smash in on itself so that the change in time increases so that the force decreases. Okay? Alrighty. A couple more applications to think about. Another one is football tackles. Okay, we kind of talked about this at the start, but if you ever see someone that has played football a lot and knows how to get tackled, they often go kind of limp when they get tackled. Okay, that's not because they're weak or anything like that. It's because they understand how to get tackled, right? If your body is more loose, more relaxed, okay, when it hits the ground, guess what? That impact time is going to go up, right? So the same thing, if time goes up, the force goes down. Okay, so we have the fat part of the equation, right? If time goes up, the force goes down. So when they do that, you'll notice they kind of go limp, and that's intentional because their body will hit the ground and it will have a longer time of collision, so the force on them is less. Okay, and that's how they avoid getting injured. Okay, if you want to get injured during a football game, tense up as tight as you can during a tackle. That's the easiest way to hurt yourself. Okay. Another application of this is rolling with the punches. Okay. Same idea. If you ever watch professional boxers, when they get hit, they don't just sit there and take it face on, right? They try to move with those punches as much as possible. Why? Same reason, right? If you can increase that time of collision, you'll decrease the force on you. Okay. So they know when they see that punch coming, if they can't avoid it, they just move with that punch to decrease the amount of force on their body. Okay. And then the last application is kind of a sad one, but it's important to understand. Okay, if you look at the reports for drunk drivers or DUIs that have collisions with other people, usually they're the ones that survive and the people in the other car don't. Okay, why is that? That's because the person that's drunk is often, again, very limp, very loose. Their body's relaxed. They don't realize what's going on. They can't tense up when they see the collision occurring. Okay. Unfortunately, the family or the person in the other car when they get hit, they're going to tense up naturally because their body understands what's going on. But because they're more tense, they're more likely to have a higher force on them, and so they're more likely to die from that collision. Okay, so it's very unfortunate when that occurs, but that's why, because of the impulse equation. Okay, all right, so hopefully between those applications and the problems, hopefully you have a pretty good understanding of what impulse is and why it's important for designing cars and all these different things. And so it's a very useful equation. I hope you understand that. Make sure you do the homework on impulse. But that's it. Hopefully that made sense. Let me know if you have any questions, and thank you for watching.